All right, today we're pulling back the curtain on AI. We're going to look at the actual engines that make machine learning, well, learn. So, how does a machine really do it? Let's dive in. It really all boils down to that one question. And spoiler alert, it's not magic. It's actually a super methodical process of trial and error, all guided by some pretty brilliant math. And the whole thing kicks off with one simple idea: figuring out just how wrong you are.
Okay, so imagine you're playing a game, and the goal is to get the lowest score possible. Ideally, 0. That's exactly what a loss function is for an AI. Every single time the AI makes a guess, the loss function gives it a score, telling it, nope, you were this far off. The entire game, the whole learning process, is just one big mission to get that score as close to 0 as it can. But here's the catch. This isn't some easy, straight-line journey. Picture this. You're dropped in the middle of a massive, foggy mountain range. Your mission: find the absolute lowest valley. This whole mountain range, that's what we call the lost landscape. And it's tricky because there are all these little dips and valleys. We call those local minima. They can totally fool you and trap you. But somewhere out there is the one true lowest point, the global minimum. And that's the prize.
So, how in the world do you navigate a landscape like that, especially when it's foggy? Well, you start with the most basic strategy imaginable. You just walk downhill. The simple idea is called gradient descent. And honestly, it's kind of beautiful. All it does is, at any given spot, it figures out which direction is the steepest way down. That steepness is the gradient. Then it takes a little step in that direction. And then it does it again, and again, and again. Just step by step by step. Slowly but surely, it inches its way toward the bottom.
Okay, but even this simple downhill walk has a classic trade-off. It's basically the story of the tortoise and the hare. On one hand, you have batch gradient descent. That's the tortoise. It is super careful. It looks at the entire set of data before it takes a single confident step. It's steady, for sure, but man is it slow. Then you have the hare, stochastic gradient descent, or SGD. It just grabs one single piece of data, takes a quick look, and boom, takes a step. It's incredibly fast, but its path is all over the place, really jumpy and noisy.
So what do? Slow and steady, or fast and chaotic? Well, you find a middle ground. And that's exactly what mini-batch gradient descent does. It's the Goldilocks solution. Instead of looking at everything, or just one thing, it looks at a small, manageable group, a mini-batch of data. And with that, you really get the best of both worlds. It's way faster than the tortoise, but much more stable than the hare. This right here, this is pretty much the standard that powers most AI today. But just walking downhill, even in mini batches, isn't always enough. The process can still get bogged down. So it was time for an upgrade, time to make our little walker faster and a whole lot smarter. So here's the next big problem you run into. That lost landscape, it's not all nice, steep hills. What happens when you hit a long, nearly flat plateau? The slope is practically 0. A basic gradient descent algorithm just crawls. It takes forever to get across these flat spots, if it ever does.
So what's the fix? You give it momentum. Think about it like this. Instead of just being a walker who only cares about the ground right under their feet, it becomes a giant, heavy boulder rolling downhill. It builds up speed, right? So when it hits one of those flat plateaus, it doesn't just stop. It has momentum. It just rolls right on across and keeps going. This helps it find the bottom way, way faster.
But of course, solving one problem introduces another one. What if the landscape is really weird? Imagine a valley where one side is a super gentle slope, but the other side is a sheer cliff face. If you're programmed to take the same size step every time, what we call the learning rate, you're in trouble. You'll take forever inching down the gentle slope, and then you'll take one giant step and fly right off the cliff. A single, fixed step size just isn't going to cut it.
And this is where things get really clever. We introduce adaptive methods. You can think of it like giving our algorithm a pair of smart hiking boots. These boots automatically know what kind of terrain they're on. When things get steep and dangerous, they take tiny, careful little steps. But when they're on a nice, gentle plane, they take big, long, confident strides. This makes the whole trip way more efficient and a lot safer.
Okay, so let's recap. We've got speed thanks to momentum, and we've got smarts thanks to these adaptive methods. The next logical question is, what if we could have both? What happens when you put them together? Well, you get an absolute all-star. So imagine we take that raw, unstoppable power of the rolling boulder, the momentum that just blasts through those flat sections, and we combine it with the brilliant adaptability of those smart hiking boots, the ones that know exactly how big of a step to take. What do you think you get when you put those two things together?
You get ADAM. It stands for Adaptive Moment Estimation. And let me tell you, ADAM is the default go-to optimizer for a reason. It's the one most people reach for first, and there's a good reason why.
See, ADAM is this beautiful combination of everything we've just talked about. It has the speed of that momentum boulder, but it also has the intelligence of the adaptive hiking boots. So what does that mean in practice? It means it converges super fast. It's really robust, meaning it works well on a huge variety of different AI models. And, maybe best of all, it's just easier to use, because you don't have to spend as much time manually fiddling with that learning rate.
All right, so we've got this whole toolkit now. SGD, momentum, ADAM. The big question for anyone building this stuff is, which one do I actually use? Let's take a look at the modern playbook. This gives you a pretty good rule of thumb. For most things, yeah, just start with ADAM. It's a fantastic choice. But, and this is super interesting, sometimes the older, simpler SGD with momentum actually wins. It turns out that SGD's noisy, kind of random path can sometimes help it avoid getting stuck in a really sharp, narrow valley and instead find a wider, flatter one. And models that land in those wider valleys often work better on new data they've never seen before. So yeah, the choice really, really matters.
And that really brings us to the big takeaway here. This whole quest is far from over. Even with a powerhouse like ADAM, that lost landscape is still a dangerous place. Researchers are still wrestling with all sorts of weird problems, like saddle points that can trap an algorithm in limbo. And figuring out the perfect settings for all this stuff, the hyperparameters, it still feels more like an art than a hard science.
Which leaves us with one last, really cool question to think about. ADAM has been the reigning champ for years now, but the hunt for something even faster, even smarter, never ever stops. So if today's AI is built on ADAM, what do you think tomorrow's AI will be built on? Maybe an algorithm that doesn't just learn, but learns how to learn? Thanks for joining me.